It is incorrect and potentially dangerous to connect the ground wire to the neutral bar in a transfer switch cabinet. In a standard electrical system, the neutral conductor carries the unbalanced current from single-phase loads and provides a return path for the electrical current. The grounding conductor, on the other hand, provides a low-impedance path to ground for fault currents and protects against electrical shocks. According to the National Electrical Code, or NEC, neutral and grounding conductors must be kept separate to maintain their distinct functions. Connecting the ground wire to the neutral bar blurs this distinction and can lead to safety hazards. Breakers do not rely on ground current to detect short circuits. They operate based on the flow of current through the phase and neutral conductors. In a properly wired system, short circuits cause a high surge of current through these conductors, which trips the breaker. In certain specific applications, such as aircraft hangars and healthcare facilities, bonding the ground and neutral conductors may be necessary to mitigate electrical noise and interference. However, this is not typically done in a residential or commercial setting. The ground wire should be disconnected from the neutral bar in the transfer switch cabinet and connected to the dedicated ground bar. This will ensure proper separation of neutral and grounding conductors and maintain the integrity of the electrical system. Grounding and neutral conductors play very distinct roles in an electrical system. The neutral conductor is the return path for current under normal operating conditions, carrying the unbalanced load back to the source. The grounding conductor, also known as the equipment grounding conductor or safety ground, provides a low impedance path for fault currents to return to the source, which facilitates the rapid operation of overcurrent protection devices like circuit breakers and fuses, thus preventing electrical shock hazards. The NEC mandates the separation of neutral and grounding conductors to prevent unintended current flow on the grounding path. If the neutral and ground are connected improperly, some normal load current could flow through the grounding conductors. This can create several problems. Firstly, it can cause nuisance tripping of ground fault circuit interrupters, or GFCIs, as these devices are designed to detect even small amounts of current leakage to ground. Secondly, it can energize metallic parts of equipment, creating a shock hazard. Thirdly, it can interfere with the proper operation of sensitive electronic equipment. Circuit breakers are designed to trip when they detect an overcurrent condition. This overcurrent can be caused by a short circuit, where there is an unintended low resistance connection between two conductors, or by an overload, where the current exceeds the ampacity of the circuit. In either case, the rapid increase in current causes the breaker to trip, protecting the circuit and equipment from damage. Ground fault circuit interrupters, or GFCIs, are a different type of overcurrent protection device. They are designed to detect very small amounts of current leakage to ground, typically in the milliamp range. If a ground fault is detected, the GFCI will trip, interrupting the circuit and preventing electrical shock. GFCIs are commonly used in bathrooms, kitchens, and other areas where there is a risk of water exposure. Arc fault circuit interrupters, or SIs, are designed to detect arc faults, which are dangerous electrical arcs that can occur due to damaged or deteriorated wiring. These arcs can generate a lot of heat and can be a fire hazard. SIs are designed to trip when they detect an arc fault, preventing a fire from starting. The location of the neutral ground bond is crucial for proper electrical system operation. In a typical service entrance, the neutral and ground are bonded together at a single point, usually at the main service panel. This creates a common reference point for both the neutral and ground conductors. This single point bond is essential to ensure that fault currents have a low impedance path back to the source, allowing overcurrent protection devices to operate quickly and effectively. Multiple neutral ground bonds can create circulating currents and other problems. In automatic transfer switches, or ATSs, it is especially important to maintain the separation of neutral and ground conductors. An ATS is used to switch between two power sources such as utility power and generator power. When the ATS is in the normal position, it connects the building's electrical system to the utility power. When the utility power fails, the ATS automatically switches to the generator power. It is vital that the neutral and ground conductors are kept separate in the ATS to prevent circulating currents and ensure proper operation of overcurrent protection devices regardless of which power source is active. In some specific applications, such as separately derived systems or SDS, like generators or transformers, a neutral ground bond is required at the SDS. This bond is necessary to establish a reference point for the neutral conductor and to provide a path for fault currents to return to the source. However, it is important to ensure that there is only one neutral ground bond in the entire system. If there are multiple bonds, circulating currents can occur, leading to problems. The NEC outlines specific requirements for grounding and bonding in Article 250. This article covers everything from the size of grounding conductors to the location of neutral ground bonds. It is essential to follow the NEC requirements to ensure a safe and compliant electrical system. Some common misconceptions about grounding include the belief that grounding is only necessary for safety. While safety is a primary concern, grounding also plays a crucial role in the proper operation of electrical equipment. Grounding provides a stable reference point for voltage, which is essential for the reliable operation of sensitive electronic devices. Another misconception is that any connection to ground is sufficient. The quality of the ground connection is critical. A poor ground connection can have high impedance, which can impede the flow of fault currents and reduce the effectiveness of overcurrent protection devices. Regular inspection and maintenance of grounding systems are essential to ensure their continued effectiveness. This includes checking the tightness of connections, inspecting conductors for damage or corrosion, and testing the impedance of the ground path. Grounding electrodes, such as ground rods and ground plates, should be installed in accordance with the NEC and should be properly sized for the system. The resistance to ground should be measured periodically to ensure that it is within acceptable limits. If the resistance is too high, additional grounding electrodes may be required. When working on electrical systems, it is important to use appropriate personal protective equipment, or PPE. This includes safety glasses, gloves, and insulated tools. Always de-energize circuits before working on them, and use a voltage tester to verify that the circuit is de-energized. Follow lockout/tagout procedures to prevent accidental re-energization of the circuit. If you are not comfortable working on electrical systems, it is best to hire a qualified electrician. They have the training and experience to perform the work safely and correctly. In summary, the separation of neutral and grounding conductors is a fundamental principle of electrical safety. Improper grounding can create a variety of hazards, including electrical shock, fire, and equipment damage. Always follow the NEC requirements for grounding and bonding, and consult with a qualified electrician if you have any questions. The National Electrical Code, or NEC, provides comprehensive guidelines for safe electrical installations. It's revised every 3 years to incorporate the latest safety practices and technological advancements. Article 250 specifically addresses grounding and bonding, detailing the requirements for creating a safe, low-impedance path for fault currents. Key aspects include the size and type of grounding conductors, the methods for connecting grounding electrodes, and the proper bonding of metallic enclosures and equipment. Understanding and adhering to these regulations is vital for preventing electrical hazards. Separately derived systems, or SDS, such as generators, transformers, and isolated power systems, require special attention to grounding and bonding. An SDS is an electrical system that derives its power from a source that is electrically isolated from the main power system. In these systems, the neutral conductor must be grounded at the SDS to establish a reference point for voltage and to provide a path for fault current. The location of the neutral ground bond is critical, and it must be installed in accordance with the NEC. Common grounding electrodes include ground rods, ground plates, and metal underground water pipes. Ground rods are typically 8 feet long and are driven into the ground. Ground plates are buried horizontally in the earth. Metal underground water pipes can be used as grounding electrodes if they meet certain requirements. The choice of grounding electrode depends on the soil conditions and the available space. The size of grounding conductors is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of grounding conductors based on the size of the service entrance conductors. It's important to use the correct size grounding conductors to ensure that they can safely carry fault current. Bonding is the process of connecting metallic parts of an electrical system together to create a common ground potential. This includes bonding metallic enclosures, equipment, and raceways. Bonding helps to prevent voltage differences between metallic parts, which can create a shock hazard. The NEC specifies the methods for bonding metallic parts of an electrical system. Ground fault protection of equipment, or GFP, is required for certain electrical systems, particularly those serving large loads. GFP is designed to detect ground faults and to trip the circuit breaker, preventing damage to equipment and reducing the risk of electrical shock. The NEC specifies the requirements for GFP. Regular testing of grounding systems is essential to ensure that they are functioning properly. Ground resistance testing measures the resistance of the grounding system to earth. This test can identify problems with grounding electrodes, connections, and conductors. Ground impedance testing measures the impedance of the ground path. This test can identify problems with bonding and grounding conductors. The results of these tests can be used to identify and correct problems with the grounding system. Electrical safety audits are a comprehensive assessment of an electrical system's safety. These audits can identify potential hazards and can recommend corrective actions. Electrical safety audits are typically performed by qualified electrical inspectors. The audit includes a review of the electrical system's design, installation, and maintenance. It also includes visual inspections and testing. Common electrical safety hazards include overloaded circuits, damaged wiring, improper grounding, and lack of GFCI protection. Overloaded circuits can cause overheating and fires. Damaged wiring can create a shock hazard. Improper grounding can prevent overcurrent protection devices from operating properly. Lack of GFCI protection can increase the risk of electrical shock in wet locations. Addressing these hazards can significantly improve electrical safety. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges. Voltage surges can be caused by lightning strikes, utility switching, and other events. SPD diverts surge current to ground, protecting sensitive electronic equipment from damage. The NEC specifies the requirements for SPD. Harmonic distortion is a type of electrical noise that can cause problems with electrical equipment. Harmonics are caused by nonlinear loads such as electronic devices and variable frequency drives. Harmonics can cause overheating of transformers and conductors, and they can interfere with the operation of sensitive electronic equipment. Harmonic filters can be used to reduce harmonic distortion. Power quality monitoring is the process of measuring and analyzing the characteristics of electrical power. Power quality problems can include voltage sags, voltage swells, harmonic distortion, and transients. Power quality monitoring can help to identify the source of power quality problems and to implement corrective actions. Energy efficiency is the practice of using less energy to perform the same task. Energy-efficient lighting, appliances, and equipment can save money and reduce environmental impact. Energy audits can identify opportunities for energy efficiency improvements. Renewable energy sources, such as solar, wind, and hydro, are becoming increasingly popular. Renewable energy sources can reduce reliance on fossil fuels and can reduce carbon emissions. The NEC specifies the requirements for installing renewable energy systems. Proper electrical design, installation, and maintenance are essential for ensuring a safe and reliable electrical system. Following the NEC requirements and working with qualified electrical professionals can help to prevent electrical hazards and to ensure that the electrical system operates efficiently. Ongoing education and training are important for staying up to date on the latest electrical safety practices and technologies.